I must have not saw all of the Zoom people from Tuesday because the list you showed me was, I must not have clicked on something.
Maybe not.
Okay, I was gonna say, because then we must have had a fair number of, unless I looked, I might have looked at it wrong. I don't know. It is what it is. All right, I got 6. We're ready. Okay, so anybody on Zoom or the 3 amigos I've got in front of me have any questions from last time? Did we start working on stuff? Granted, don't drag your feet. Okay. It's not going to be good if you drag your feet. It's better to practice it as soon as you can. All right. Well, our list today is operation with radicals, add, subtract, multiply, divide. A lot of simplifying that goes in these two before you can add or subtract. It's basically adding like terms once you have like term radicals, which might mean you've got to simplify first before you can add or subtract. The multiply divide part is just that. You're looking at multiplying. You can multiply any radicals you want together as long as they have the same index. There is a couple of questions in, I believe, the one on dividing, where they make you go from a radical expression to a rational exponent. The indexes are different. That's basically what we did at the end of Tuesday, where we were adding 2 expressions that had different fractional exponents. We had to find a common denominator, add them. Basically the same thing. They just start out looking like radicals. We change them to exponents, and then we add them together and then rewrite it. So it's a manipulation of things following some rules. It's not all that bad. Rationalizing denominator is an important concept that we need to cover. There are also some divide problems that have quantities with radicals. Okay, so what you're going to see me do is approach it like difference of squares pattern, and we're going to use what's called the conjugate. They look exactly the same. We do first and last only, gets rid of the radical. The radical equations, many of them are very, very fast. Some of them are going to be quadratics. The quadratic ones need to be factored, and then oftentimes there might not be 2 solutions. One of them might be the extraneous version that you have to throw out because it just doesn't work. Okay, and if I remember correctly from last year when we were on Zoom doing these, and I was sitting in my family room, there is at least one radical equation that is going to be like the never-ending problem, where you've got 2 radicals, you get rid of one, but you generate another one, then you got to isolate that and get rid of that one. It's a really long problem. That typically I'd put on as maybe like a bonus problem max. I will not make you do one of those never-ending problems as one of your quiz problems. Okay, so our quiz is next Tuesday, covering chapters 9 and 10, but we're not going to get to that. We're just not going to get to complex numbers. I'll just do it after the quiz the following or next Thursday, and then go into the stuff in chapter 12 on exponents and logarithms, and it's not that big of a deal. Okay. We already did a little bit of it, didn't we, Hannah, with when we did the quadratic formula and complex roots?
Yes.
So this would just be more of the same, simplifying square roots of negatives, but also working with complex number operations, which is kind of a FOIL thing. So anyway, so off we go. Okay, so add, subtract, multiply, divide. You have to have like term. Let's just do add and subtract first. So we're going to add or subtract radical expressions. In its simplest case is kind of like this. Okay, I can't add these together because they're not like terms. So I can't add these together because they're not like terms. It's like having 3x plus y. You can't add them together. They're not like terms. So all of the problems that are in the add or subtract radical section, I believe is section 4, they're going to look like they're not something you can add or subtract, but they're not simplified yet. So there has to be some simplification. Okay, and the other part of this, which is just a real manipulation of adding like terms, there's going to be numbers and variables out in front of those radicals that also have to be like terms. So if you see things that aren't alike, either out in front or underneath, then chances are either you can't add them or you didn't simplify something correctly yet. Okay, it's got to go further. So there's a lot of built-in, I guess, little miniature check things that will help us. I'll start with a square root first. I won't do the very first problem is a cube root, but I don't want to do a cube root first. Okay, so this is a subtraction problem. So I've got the square root of 50z minus the square root of 8z. Obviously not the same. 50z and 8z are not the same. The z is okay, but I've got to simplify the radical by pulling out perfect square factors. Then whatever's left underneath has to be the same, and then I can just manipulate whatever's in front. Okay, so going back to what we did on Tuesday, we're going to take and we're going to break down this as 25, 2, and then the z. We're going to break down the 8 as a 4 and a 2 and the z. We're going to pull out the square roots of 25 and 4 respectively. And now when I do that, the expression under the radical, both being exactly the same, they're now like term radicals. And I can then just deal with the coefficients that are in front. 5 minus 2 is 3. Square roots of 2z. So, it goes back to what I've said many times over. You can multiply anything you want to. You can't add or subtract anything you want to. They have to be exactly the same. Okay, so many of these are going to be, you have to simplify first, then you can add or subtract. Okay, and every single one of them that's an addition or subtraction problem should be able to be simplified so that you can add or subtract them. I haven't seen one to date where it's not something you can simplify. And you just have to be cautious. You just have to be really cautious. Now, the other thing that happens that sometimes students make mistakes on, numbers out in front of this radical and expressions out in front are being multiplied to their radical. The only add or subtract is here. So when you take out a number, let's say I had 3 square roots of 8, and I took the square root of 4 out, okay, that gets multiplied to the 3, not added. The add is right here. So you have to be really cautious about not adding what you're taking out to the things in front. It all gets multiplied, even if it makes the exponent go higher. Okay, so what can we take out of this 20w cubed? So like we can take out, what are we breaking the 20 into? 4 and 5. And what about the w cubed? We're going to break it down to even and 1 remaining. Okay. Now this, I'm going to just rewrite this, even though there's nothing I can break down. I just want to rewrite it so I can pay, be careful. So that's going to come out of there. And then we're going to bring out also a factor of w. So that brings us 2wu, because the square root of 4 came out and half of the 2 came out, leaving me with radical 5w. Okay, so the 5 and the w are not going to come out of there, but then the u is. So that leaves me with 7w. WU 5W. Okay, and what I said just a few minutes ago, not only do the expressions under the radical have to be identical for you to add the things together, the things out in front also have to be like terms before you can add them together. So you got a whole boatload of like term things going on that if you don't have like terms, maybe you didn't simplify something correctly, it's unlikely that they give you a problem you can't work with. You just have to be careful. Okay, so then we'll just add these two together. And then we've got the square root of 5W. So it's kind of hard. I guess it would be hard to say, well, I don't know what to do because I don't have them alike. That means you just didn't simplify something the way you should have. Okay, any questions so far? That's basically the drill for quite a bit of section 4. There are a few things that are a little different. We'll do some cubed roots, but section 4 is a lot just simplified so you can add them together. Let's do a cubed root. There's a couple of cubed roots in here. Okay, that doesn't change the problem. It just changes that we're looking for, remember, numbers out of a different list, and we're looking at groups of 3 out of the variable things. Okay, so this is a subtraction problem. Cubed root of 81x to the 4th. So now what I'm looking for is, see, 2 cubed, 3 cubed, 4 cubed. That's going to be big enough. And then if I don't have equivalent expressions under the cubed root, and I don't have equivalent, like terms in front of them, then we're not adding these together or subtracting them in this case. Okay, so 24, looking at it, my perfect cube list, 24 has a factor of 8. So this is just a process of breaking it down, so we're careful. Cubed root, I want to make that x to the 4th a group of 3 and then a lonely x to the 1st. Inside of 81, there is a factor of 27. There's kind of a hint. I mean, if you can simplify 24 to 8 and 3, the 8's coming out, the 3's not, so 81's got to be something with a 3 in it. There's just, again, something else that helps you say, okay, I know how to do this one. Seeing this number being left and that one coming out means I've got to have that number left over there or it's not going to be the same. So that's staying, and so these things are staying in, and then we're going to pull out the 8, and we're going to pull out the x. So we get negative 2x on the outside. Okay, cubed root of 8, 2. 1 group of 3. So cubed root of x cubed is x. That's going to be on the outside. And then the 3x's left inside. Okay, we're pulling out the cubed root of 27. What are we going to do with it with that 2? We're going to multiply it. So that 3 coming out gets multiplied to the 2. And then again, that cubed root of x, oops, that's a cubed root. And then 3x. And once again, okay, do we have the same thing under the radical? Yes. Do we have like terms in front of the radical? Yes. Okay, then you can combine them. Negative 2, negative 6 is negative 8. Cubed root of 3x. So the cube roots aren't much different than the square roots. You're just looking for different groupings of your radical of your variables, different set of numbers for the numeric values. And again, the list I gave you and that factoring stuff with perfect squares and perfect cubes, I would just have that as a reference. Okay, I'll give you a couple to work with here for a second. So 2x square roots of 32x plus the square root of 8x cubed. So we'll do a square root. And then about the negative cubed root of 24 plus 4 cubed roots of 81. This one doesn't even have any variables, just has numeric values. And let's do one more. Let's do also radical 24W plus radical 54W. We'll do 3. And that'll essentially put section 4 to rest. It's more about simplifying and just making sure you get like terms than it is anything else. Well, Hannah, I gave some thought to your question too.
Okay.
We'll just talk about later quickly.
Yeah.
Hey, how we doing? Okay. Almost done, yeah. I should interact with these Zoom people more, hey? Should get them involved. Hey, Logan? Yeah, call them out. Ah, someone's got an answer. Yeah. Yeah, I'm not the best. Sorry, Jade. I'm not the most savvy with the Zoom thing, unless that's all I'm doing. I'm trying to multitask. I'm not gonna multitasker. So, Jade, do you have an answer for this first one? Are you putting it in chat? Gotta unmute if you're gonna answer. Anybody else have an answer for the first one? Oh, that's the Okay. Anybody on Zoom want to share any of the ones they got? Oh, here we go. What do we got? What do we got? 10x square root 2x. Yep, that would be the first one. My microphone is, 10. Yes, it is 10x squared of 2x, Jade. Yes, it is. Good. Yes, it is. So we're going to take out the square root of 16, which comes out as 4. So that's where the 8x comes from. So we're taking the square root of 16 out of here. We're taking the square root of 4 out of here. And we're taking an x out. So that is 2x square roots of 2x. So you get 10x square roots, 10x square roots of 2x. Yes, good. I wrote that not facetiously, but as a way of saying, look, you got to be careful because that is such an easy thing to see. It's like, holy cow, no, okay, careful there. We don't want that. 5 square root of 6w for the next one. I think so. We're going to take out the square root of 4. We're going to take out the square root of 9. So you've got 2 square roots of 6w plus 3 square roots of 6w, which, yes, is 5 square roots of 6w. Good. You have to, these are the things that need to make it to a note sheet for a quiz or an exam. These are the types of things that, the things that are easily done incorrectly unless you do enough of them. Same thing with factoring, like x squared minus 1 is not, factors to x minus 1x plus 1. 10 cubed root of 3 for the last one. Probably, I think so. Let's see, what are we taking out of here? We're taking out the cubed root of 8. We got a 4 in front. We're taking out the cubed root of 27. So we're going to have negative 2 cubed roots of 3. Plus, we take the 3 out and multiply it to the 4, 12 cubed roots of 3. 4, 10 cubed roots of 3. Good. Awesome. Any questions about adding or subtracting? Multiplying is so much easier. Adding and subtracting, I'm serious. Adding, subtracting anything, rational expressions, polynomials, you name it. Adding and subtracting fractions is not is not easier than multiplying or dividing. Okay, well, the multiplying and dividing are going to be, well, it's usually multiply first, simplify after, or in some cases, the divide, you might be able to simplify. Most of the things I have in front of me right now in section 5 are just multiply, 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 multiply. We're just going to multiply a whole bunch of things together. If the index is the same, you're just going to shove it together and simplify. If it simplifies, some of it doesn't even simplify. So we're using this property that I had written down on Tuesday. We're essentially doing this. And I could put a little n in there for, doesn't matter what root it is, if it's cubed root, fourth root, fifth root, square root, as long as the index is the same, whatever's underneath just gets multiplied all together, and then you just simplify what you got after that. Okay. So for example, numeric, these are just numeric at first. I'll just write a bunch of them down. You get the square root of 21 and the square root of 3. You've got the square root of 80 times 3 square roots of 12. You could simplify some of these beforehand, but I would just wait until you're done. Let's say you have 2 square roots of 12 times 5 square roots of 6. None of these should be simplified first. These are not add or subtract. My suggestion would be make it a big problem. This one's going to get a little bit big, but I don't think it's bad. Okay. And I'm going to show you what I'm going to do with this one that I think makes it even easier than if I just made it really big. Okay. So 3 times 21 is 63. Now I'm looking for perfect square factors. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect square factor of 63 is going to come out as 9. Okay. The other thing I would be obliged to tell you, if you have a good scientific calculator that does radicals and has what's called a math print or classic print or whatever it is, a TI-30X2A multi-view or whatever it's called. Some of them simplify radicals. You can check these all day long and it does it automatically for you. Okay, so make it big, simplify. This one is radical 80 times 3 radical 12. Here's what I'm going to do with this one. I'm not going to multiply the 80 and 12 together and call it 960. And the reason I'm not going to do that is because finding a perfect square factor of 960 is harder for students than finding a factor inside of 80 and finding a factor inside of 12. So I'm not going to make it 960. I'm just going to do like we did with all those other things with like W cubes and X to the fifths and things like that. Just tear down the 80 and the 12 individually and treat it as if it were like a W and a V. And do it that way. So I got to just see, all right, what's inside of 80? Well, we could start at 49. 49 doesn't come out. I could ask one of the Zoom people. Perfect square factor inside of 80. Whose turn? Jake. Perfect square factor inside of 80, dude. No. There's 80. 12's easy. Okay, so we can treat that 80 and 12 instead of it being 960 and looking for that perfect square, just breaking down the numbers individually. You're still going to take out the square root of 16 and multiply it to 3. You're still going to take out the square root of 4 and multiply it to 3. So we're going to multiply a factor of 4 and a factor of 2, so a factor of 8. And then the 5 and the 3, since they're under the radical, we don't leave them as 5 times 3, we just make it 15. Same thing here, okay? Although I think multiplying 6 and 2 or 12 and 6 together isn't going to cause us that much of a problem in finding a perfect square factor inside of 72. You just have to make sure that when you bring it out, it gets multiplied to what's in front. Okay. Now, the other thing I think is worth mentioning, if you type that into your calculator and turned it into a decimal, and you type this into your calculator and turn it into a decimal, they're going to be the same. If they're not the same, then try the problem over because you didn't do something correctly. Okay. So those are just numeric. Any questions on what we're doing? Now we add some variables or change the index. The game is not going to change. It's the same thing. Okay, let's stick with some square roots still. Square root of 6b, 3b cubed. I'll let you do that. I'll give you a couple of them actually. 2x cubed y and 8x to the fourth y. Why not? Now let's see what you do with the cubed root. I'll give you a cubed root. Why not? I have faith in my class. Give me a chance to stamp and stretch. People on Zoom, feel free to type out any one of those answers and throw it in the chat. We'll take a look. Oh, someone's got one already. Probably the first one. The first one was easy. I gotta learn how to do this whole breakout room thing.
Yeah.
I don't know how to do that.
It's also hard to do when we're in like hybrid.
Oh, yeah, I suppose. Where did that go? How do I get back to that? Oh, here we go. 3. There shouldn't be there shouldn't be a square root in the first one. It should just be an expression. Oh, no. I'm sorry. You're right. But the b squared should be on the outside. I think you got your square root in the wrong spot. I think you got the right idea, but I think you got the b squared in the wrong spot. Fixed it. Yeah. Oh, yep. 3 square root 2. I think that's what you meant. It's hard to type stuff in a computer mathematically. Okay, so I'm just going to shove these together while we're working. So 16x to the 7th y squared. This is going to be the cubed root of 81 y to the 13th, which it doesn't hurt to break these down. 27, 3, 12, 1. Well, 16, 6, 1, and 2. That's in my way. That's the other thing about this multitasking with Zoom. I always end up hitting the Zoom bar or doing something crazy. Yes. Oh. Well, all I have to say is it's Thursday. I was just checking to see if you were paying attention. My bad. 108, still 27, but it's 4, not 3. Sorry about that. That makes more sense, eh? Yeah, 81. I don't know. Thursday. So, got any more? So let's see, we got 4 4x cubed y square root of x. Is that it? I think that's it, hey? Yep, that's it for that one. And this turns into 3y to the fourth cubed roots of 4y. So yanking those out of there, and those are staying in. That's multiplication. There's a few more things that are in this multiplication section, but those are primarily just the ones that you have to simplify, the ones that you have to make a large problem and then look for perfect square factors and continue to do it that way. There are a few other things we're going to do here in this section of multiplication. But primarily, it's just, even though it's a multiplication problem, it's radical themed, and you just have to be careful to apply the properties of radicals correctly as you go through and multiply the things that we're going to multiply. Okay, some of them are just distributive property problems. Okay, so, and they may end up needing some simplification, but that doesn't necessarily mean that we're going to be able to turn it into anything super nice. Okay. So there's one that looks like this, and then believe it or not, there are a couple foil-based themed problems that are really just manipulation of radicals. There isn't really a practical application to that. I'm going to be honest with you. Okay, there are some things that you run into in some of the polynomial things if you end up in pre-calc or 111 in terms of multiplying weird things like complex numbers, but they don't look like that. These are not complex numbers either. Okay, so this is just a distribute problem. So we're going to multiply into the quantity. So it's a multiplication problem. And 5 times 15 is 75. And 5 times 6 is 30. Because they're both under radical. Anything under a radical can be multiplied together as long as the index is the same. Okay? Numbers out in front of the radicals are going to be multiplied together because they're out in front of radicals. Now we can simplify this one because inside of 75 is a 25 and a 3. So we can bring the 5 out and multiply it to the 9. And the 3 is going to go there. But there aren't any perfect square factors inside of 30. And I can't change it to radical 10 and radical 3 and pull a 10 out because that's not, that just doesn't work that way. So that's it. You can only simplify the square root of 75 by taking the square root of 5 out and then multiply it to the 9. Like I said, it's an exercise in working with radicals and simplifying radicals. Nothing more. Okay, I'll call a spade a spade. This one is a FOIL problem. So carefully, these are the ones where you just have to be careful because there's so many moving parts. I mean, if it were X's, it'd be different. They're radicals, so you just have to be really cautious. I don't do these ever in just by trying to, sometimes the FOIL with polynomials, I can do it without having to really write anything down. These get a little bit too busy. So we'll go through the first. First is the first two. So we get 24 square roots of 10. Some of this might simplify. Okay. Our outside are those two. Okay. Now that's a negative on the 8, so it's minus. 6 times 8 is 48. What about radical 5 times radical 5? That's the definition of a square root. So the definition of a square root is you got the same number underneath. That's just 5. Likewise, when we go to the inside, I'll go a different color on the inside last. So the inside is minus 2 radical 2 and 4 radical 2, which is minus 8 times 2. Because I've got the 2 times 4, and I've got 2 square roots of 2, which is 2. Again, that's what a radical means. And then the last, since they're both negative, negative here, negative there, positive 16 square roots 10. Okay, this simplifies down nicely. But again, it's just something you got to be really cautious with to do the few things that it takes to get to the 4 terms and then just simplify the 4 terms. So we've got how many radical 10s? How many total? Got 24 here, 16 here, so 40. I'm not sure how they're going to want this answer. I'm going to assume that the numeric value is going to go out here. So we got negative 48 times 5, which is negative 240. And then we've got negative 16, which is negative 256. So that one there and this one here means that right there. You know, I don't know. I don't know if they will balk at this. I mean, they're both correct. I mean, if this was a quiz problem, and you gave me, you know, this version and the system said, no, 0 points, I know better than to not accept that. So that's why you always submit your work. And I just override that system. So just a big FOIL problem. Here, I'll give you one to try. And then we'll do a couple more things on this before we get to divide and then equations. I'll make them somewhat simplifiable. That turned out to be something special. I didn't intentionally do that. You have to understand that my examples are not that, I don't think about them deviously and so it's so quick that they come out. They never end up being nice. I tell my Algebra 2 kids all the time, if I make a system where it comes out to be 2 integers, we're leaving early today, it always comes out to be something like 7/11 and negative 3/11, and it's never an integer unless I really think about it. Did you get negative 34? Yeah, I didn't do that on purpose. I promise. I didn't do that on purpose. First, 2 radical 3 is 6. Outside, 4 radical 15. Yep, that's exactly right, Isabella. Inside, minus 4 radical 15. Last, negative 8 times 5. So 6 minus 40. I didn't do that on purpose. I swear I didn't do it on purpose. Okay, well, kind of sticking with the same theme, I guess, because of this outside-inside thing going away. There are 2 problems in this section before we get to the hardcore radical rational exponent thing that look like this. One of them is a difference of squares pattern. So you just have to see, I guess to see the forest for the trees. You've got a multiplication problem, but they're identical, except for one is a plus and one is a minus. They're identical. That's your difference of squares pattern. Your difference of squares pattern pops up in all kinds of different applications of things. And if you continue to recognize it for what it is, you don't have to do your outside and your inside at all. You just got to do your first and your last and you're done. And there's a subtraction between them. Okay, so always pay attention to that because it surfaces in different places. So it's just going to be radical x times radical x minus 4 times 5. So 2 radical 5 times 2 radical 5 is 4 times 5, which is 20. Okay. There's also one tagged in the same type of problem that's radical based. That's not the same, but it's similar. And it looks like this. Okay. And the most common error I see in students who do this problem go, oh, well, that's not bad because the squaring just undoes the radical. That's just x plus 5 because you can do this. Nope, it doesn't. You can't do that. You can't put an exponent into a quantity. You can only put it into a bunch of different factors. Okay, so that's not it. Get rid of that. Get rid of that. It's not it. It is 2 factors of this. And I would prefer probably to watch you do 2 factors of the same thing and go through FOIL carefully than to attempt the perfect square factor or perfect square pattern and not do it correctly. Okay, you're going to get something you're going to be able to add together, but you just got to go through it carefully. Okay, so first terms is going to be x. Outside is, because they're both under a radical 5x. Inside's also radical 5x. And then the last is going to be radical 5 times radical 5. And then you can add these 2 together. But it's not radical 10x. What is it? X plus. So what do you get when you add these 2 together? 2 of them. Yep, 2 of them. So it's a perfect square pattern. When you square something, you generate a perfect square. But I would really be, I wouldn't direct you that way unless you do a lot of them and it's just second nature. I would just it'd be safe to just write out 2 factors and use FOIL. So you do have a couple of radical things that are special cases. One's a perfect square or difference of squares pattern. One's a perfect square pattern. Okay. It's just, again, manipulating radicals, multiplying together, simplifying what you can simplify. Okay, the last two problems in this section before we jump into dividing and then equations look like this. I can't use an eraser to write. And the directions are write in simplified form with at most one radical. So I'm just going to say using one radical because that's what at most means. With at most one radical means 1. Okay, but the indexes are different. So in order to do this, we have to go to rational exponents, which are going to be fractions without a common denominator, add them together, find the least common denominator, add, then we're going to rewrite it. Okay? So what we need to do is remember that if you have a radical, an index on the outside, an exponent on the inside, that turns into, like we did on Tuesday, your index is your denominator and your exponent is your numerator. So this is your denominator. That's your numerator. Taking that into consideration, so index on the square root is 2, exponent is 1. This is w to the 1/2. Okay? This is w to the 2/7. This program seems to like sevens. We had a whole bunch of sevens on Tuesday. What's going on? Okay, so now I've got to find a common denominator. So we did that. Now we got to do this, which for 2 and 7 is 14. Rewrite them. Half is 7/14. How many 14ths is 2 7s? Seven goes into 14, 2, yep, 2 times 2 is 4. And now I can add those together. So since I'm multiplying, what do I do with the exponents, the 7/14 and the 4/14? What do I do with them? We only multiply when there's parentheses on the outside. So this is an add together. So you're multiplying like bases, you add the exponents. Check. Now we write it as going backwards this way. Okay. So your index is the 14 and your exponent is the 11. So it's an exercise in a couple things. Recognizing how to go from a radical to a rational exponent and vice versa. Okay, finding a common denominator for those two rational exponents and then combining them and then rewriting it again. Now, can this be simplified? My index is 14. I got to have at least a group of 14, right? Okay, so I can't simplify it. That's done. Okay, here's one that involves a similar type of thing. It's a quotient, but it's the same process. And a little birdie told me that one of these also will probably not make it to your quiz. It's just a little bit too hardcore. Okay, same thing. Okay, this is even worse, to tell you the truth. I've got AB to the 6th, and I've got the 6th root of AB, and I've got to do the same thing, write in simplified radical form with at most one radical. Well, the first thing I'm going to do is I'm going to do this. That's 8½ But since this is a square root, what can I do with this b to the 6th? Can I take it out? Can I call that b cubed on the outside? Yeah, you can. Okay, so there's that. Now we've got this a to the 1/6, and we've got this b to the 1/6 because they're both under the 6th root. So I can separate it. So what I'm doing is this. I'm just yanking it apart so I can do that. And the reason I have to do that is because these are separated. So it's just, you got to break it apart into little bitty pieces. And now we've got to subtract, and it's going to turn out to be a numerator, no denominator. And then we're going to rewrite it with a radical. So we have to subtract 1/6 from 1/2 and get a, and then we've got to subtract 1/6 from 3 to get the exponent on the b. Okay, and I'm going to say, in fact, keep it unreduced, because you got to write, because it's got to have the same index. Okay, so it's got to stay unreduced. So 1/2 minus 1/6 is 2/6, but I'm not going to call it a third unless this one simplifies to something that could be a third. So I'm going to leave it as 2/6. Okay, understand why? I can't rewrite it as a radical with an index unless it's the same denominator. So I don't want to do that. And then 3 is 18/6, and we're going to subtract off 1, and that means 17. Well, that doesn't reduce down to some bizarre number of thirds, does it? Okay, so now I can put it back to a squared and b to the 17. We're playing bingo. All right, can we simplify that? Are there any groups of 6 in there? Yeah, there's 2 groups of 6 in there. So we can actually simplify this one by calling that 12 and 5, and then taking out those. Okay, so yes, they're radicals. They ended up in this section for, I guess in working with the rational exponents, they're kind of a product thing. Again, it's just manipulation of some rules, bizarre as they may be. Okay. How are we doing? Any brain hurt yet? A little bit? Okay, that kills add, subtract, multiply. Divide rules are basically the same. And I think most of the division problems, there's not too many of them. We'll do the division and then the rationalize. There's only a couple of division and there's a bunch of rationalize. So when you divide radicals, if it seems like a smart thing to do, separate. I always check numerator divided by denominator. It could be a good thing to do. Anytime denominator, anytime the numerator is a larger number than the denominator, regardless of which form it's in, if it's in under a radical as a fraction or 2 separate radicals as a fraction, I always check, is it, if I divided the numerator by denominator, would it turn into a whole number? If it does, you should do that. If it doesn't, then don't. Then you've got to simplify something else. If you end up with a radical in the denominator of any kind, then we have to rationalize. Most of the things that are in this division section are going to turn into rationalized problems because that's something that you need to know how to do. Okay, so my comment about here, check numerator divided by denominator, would be absolutely appropriate for this one. Because if you divide 28 by 7, you're done. You can simplify the square root of 28. You could do it this way. That's legit. Common factors, you still end up with 2. But if you always check numerator divided by denominator, and it turns out to be a nice thing, then you just saved yourself a whole bunch of misery of doing something like that. Okay. The other type of division problems are just kind of simplify. And remember, always remember, you can't cross off parts of sums or differences unless you can cross it off from everything. Okay. So let's say we had something looks like this. I gotta think for a minute. Hang on. Yeah, maybe let's do something like this. Okay. So this problem on the left, I need to simplify radical 72. So we're going to take out the square root of 36. And that gives me that. Okay. So just simplifying square root of 72. Can you reduce this at all? Yes. Okay. Here's when you have a fraction, and this is a term like the quadratic formula type things. When you've got a quantity numerator and a single factor denominator, or vice versa, okay, or vice versa, if you can take a common factor out of each part of the quantity and your denominator, only if they all share something, not 2 of them, okay, not 6 and 14, but not, there's a 5, we'd be saying no. But if all 3 of them share a common factor, in this case a 2, then you can reduce the problem. If you can't take a common factor out of the number in front of the radical or anything else that's exactly the same, then you can't reduce it. So if that would have been 6 square roots of 2 minus 3 divided by 14, yes, those have a common factor. But that one doesn't, so we're not reducing it. All parts of a quantity or nothing at all. Okay, this kind of goes back to my first comment about a division problem. I could simplify radical 150. I could break this apart, but it's much better to divide 150 by 3. And now all I have to do is simplify the square root of 50. And that's just the safest thing to do. If for some reason it doesn't simplify that way, then we got to do something else. Then we can't do it. So if I would have had, well, something that looks like this. Five divided by 3 doesn't work, does it? In any other problem that would be like that, okay, so maybe I had 2 square roots of 7 divided by the square root of 2. These are rationalized problems. Without going into too many specifics and showing you an example, why do we rationalize the denominator when we got a calculator that does all this stuff for us? Well, the process of rationalizing goes back to pre-calculator. I have to come up with a decimal answer in some application, let's say Pythagorean theorem or some trig function or something. And I can't technically divide these as decimals because you've got a non-terminating, non-repeating decimal on the outside of the division. So the concept of rationalizing to make sure that the denominator was a rational number versus an irrational number because it terminates as a decimal. 9 times out of 10, you want to just use the number that is sitting in your denominator. So we've got to get rid of this radical 3. What I'm going to use is radical 3. All we're doing is multiplying by 1, but it's as in the form of radical 3 over radical 3. Combine the 5 and the 3. Radical 3 times radical 3 is 3. So if I had to turn this into a decimal value, 3 going into, the square root of 15, 3 point bunch of icky decimals, that I can do. I can't do that. It's impossible. Okay, without a calculator. Same thing over here, but this is going to reduce. So pay attention to these numbers that are in front of a radical like this. If it's even and you end up with something, you may end up having to or being able to reduce this. So once again, I don't really have a choice. I don't have any other numbers I could use. So we'll just do radical 2. And then you've got 2 square roots of 14. But since I've got a factor of 2 here and a factor of 2 there, I can cross those out. 14 doesn't simplify. Okay, what do we think about this problem? Whoops, I'm sorry, Logan, did you not? Is that too fast? All right, thanks. I wasn't sure. So you're looking over there and I wasn't sure if I did something too fast or what. What do you think about this one? Certainly 3 divided by 2 can't do, right? So just separate it and then rationalize it. Also keep in mind that numbers under a radical and numbers not under a radical cannot be reduced. I can't take a common factor of 2 out of there. I can't call that radical 3. I can call this radical 3, but that's not, okay? So just be careful. I see that sometimes too. People crossing out factors under radicals with factors from not under radicals, and it turns into pandemonium. Okay. All right. How about you give this a shot? I'm gonna add a little twist to it. Why not, hey? And how about something like this? Then we have a couple of quantity-based rationalized ones. And then we'll be into some equations, which, well, unfortunately, we're going to be, we'll be out here by 8:30. Kidding. But it's going to be 20 to 8 for sure. I guess I have some thoughts on another problem too, I guess. I just want to address something like that too. Check in with the Zoomers. How we doing? We good? Any questions? Oh, lots of fanfare. Yeah, feel free, anybody feel free to just shoot a answer into the chat. Just send her in. I know it's hard to type that stuff in, but shows me you're not sleeping. Not yet. We ready? Elizabeth said yes. Gwyneth, you ready? Zoom crowd, you ready? Where'd you go? My computer doesn't work for us. All right, Mr. Heinzman, what do you got for that first one? Thumbs up, okay.
Square root of 21y over 7y.
That looks good to me. Square root of 21y over 7y. By multiplying, I'll squeeze it in here. Square root of 7y. That's it. No reducing. Yeah, variables. Hey, if they're under the radical, you got to have one of those too. Otherwise, they don't come out. Okay. And this is, I'm just encouraging always the practice of divide. Always the practice of divide. If it's larger and it turns out to be a whole number. If it doesn't turn out to be a whole number, then, well, we're not doing that. But I could have separated that and said, oh, that's 8. And, well, what's inside of 192? 64. Okay, any thoughts on this? Square root of 3 over 2. For the last one, Jade? 3 over radical 12? Maybe, yeah, yeah. Yes. Well, yeah, you can do you answer the chat. You're co-host. You answer the chat. All right. Did you multiply by the square root of 12? I guess the reason I wrote this is I wanted to emphasize, look, I just got to get rid of the square root of 12. I don't care how. If I generate any perfect square, it goes away. I'm going to use the square root of 3. I'm not going to use the square root of 12. And the reason I'm using the square root of 3 is because that right there is the square root of 36. And it's now really simple. Because if you use the square root of 12, the square root of 12 technically has a perfect square factor of 4 in it. Now, sometimes you can't do this. If it was the square root of 8 in the denominator, I'd use 2 and get the square root of 16. So you can use whatever number you want to rationalize, as long as you get rid of the radical. As long as the radical goes away, you're good. So think about that. That might end up happening at some point. Maybe. I don't know. All right. Got to minimize you guys for a minute. Can't minimize anything. Why can't I minimize anything? My computer is defective. Oh, there we go. Maybe it's this tablet. That's dividing. No, it's not dividing. We're not done yet. Oh, shoot. Yeah, we're not done yet. Because we have something that looks like this. And maybe something that also looks like, ooh, some of these are ugly as ever. This. These are ugly. Very ugly. These are rationalized problems. And earlier I had mentioned the concept of difference of squares pattern. Okay. And the concept of conjugate denominator. That's going to be the process for these. When you've got a quantity in your denominator that's got a radical or two radicals and you got to get rid of it, you have to use the conjugate to get rid of it. So it's this difference of squares pattern. A quantity that's looks exactly the same, that made a mess, but has the opposite sign. So to get rid of this 7 minus 2 radical 5, I'm going to use 7 plus 2 radical 5. It's that difference of squares pattern. Okay. The denominator is first and last. Don't do the outside inside. You're just wasting your time. Okay. So 49 minus 2 radical 5 times 2 radical 5 is what? 4 times 5. So it's 20. Okay, so 2 radical 5 times 2 radical 5 is 20. This is just distribute. 21 plus 6 radical 5. It shouldn't reduce anymore. All it is an exercise in applying the concept of conjugate denominator difference of squares pattern to get rid of a radical quantity. Okay, that's just what has to happen. Okay. Now, this one, same type of concept, but you've got two radicals, but the conjugate is just, again, exactly the same, but it's a subtraction instead of an addition. So it's 2 radical 5 minus radical 11. And that's what gets rid of it. Okay, so you gotta be really cautious. All right, I'm gonna let you simplify that. So see what you get when you simplify. The denominator, again, in a denominator, just do first and last. The numerator, unfortunately, you gotta go through all of the FOIL algorithm. Well, I'm glad I didn't include complex numbers, Hannah.
Yeah, seriously.
Well, I don't think I've been rushing through. We'll get some equations in there. We may have to do some of the equations after too. I mean, I think I can do some of the basic ones. I just won't do the hardcore ones. And I'll just remind me when you send the attendance to put the due date for the 7 and 8 to change that so I don't forget, because it's going to be due before the quiz, and I'll just change the deadline on those. I might put a simple radical equation in the quiz, but I'm not going to put anything that's going to be miserable. There's just too much stuff on here. But we still have time.
Yeah.
We still got a lot of time. So I'm not worried about it. I guess I probably should do this too. I don't know what the answer is. I know what the denominator is. Right?
It'll simplify.
Yeah, the denominator simplify. There's the denominator for now, isn't it?
That is it for now.
Okay. So the numerator ends up being a nice simplifiable thing?
Yeah.
Cool. That doesn't happen usually. This is one of Alex's problems, so thank the Alex gods. Oh, we have 2. Seven minus square root of 55 over 3. Square, I'll square the other one. Oh, yeah, okay, it was the second one was a yes to the answer. Okay, let me just start writing it down, because we got 10 minus the square root of 55 minus 2 square roots of 55 plus 11. And then you can combine the 10 and the 11 minus 3 square roots of 55 divided by 9, and you yank out a factor of 3. 7 minus the square root of 55 over 3. Good. Yes. Good. Okay. It's just computational things with radicals. It really isn't anything more. Just be careful. Things you can't do in your head. So just be careful. Okay, we are going to do a few radical equations. I'm just going to do the few that will, like the first part of section 7, the simpler ones. And what I'll do is I'll extend section 7. I'll make sure 7 and 8 deadline for those are way off into the future. I'll probably give you a not too terrible of a radical equation on your quiz Tuesday, but it won't be, too hardcore. It may involve a quadratic. I don't know. We'll see what we do here. So radical equations are going to come in a couple of different varieties. The key to solving depends on what type of radical equation it is. Okay, if there's one radical on one side, numeric value on another, or radical with stuff added or subtracted, numeric value on another, you just want to isolate the radical. Once you isolate the radical, if it's not already isolated, square both sides, and you've got a sentence that will solve it literally very quick. So to get rid of a radical, we square both sides because they're inverse operations. And in most cases, if you've got a linear sentence, which is a linear sentence underneath your radical, you're essentially done. Same thing over here. Got rid of the 2, square both sides to get rid of the radical, and now just solve. Add 9, divide by 3. So always isolate your radical. then square. If you have radicals on both sides, that's also equally as simple. Okay. That too is just square. So it eliminates the radical. And then you end up with the sentence underneath that again is very easy, linear sentence to solve. Subtract 6y, add 15, and of course divide by 2. So once you get rid of that radical, what you should be looking at in most cases in those examples is you end up with a linear sentence to solve. Okay. There are going to be some that will generate quadratics. Produce quadratics. Those have to be factored and then check your answers. You check for extraneous answers when you generate a quadratic in solving, whether it's a radical equation, rational equation, doesn't matter. You got to check for extraneous answers. Numbers that come out that don't work. Okay. So something like this is going to generate a quadratic. I've got a radical on one side, which is isolated, so it's isolated. I don't want to do anything with it. But on the other side, I either have a variable or a variable quantity. And when you square a quantity, you're going to produce a quadratic. You're going to produce a perfect square. So in this case, and I'll do another one that's like it, when I square both sides, while I get rid of the radical on the right side, I produce a quadratic term on the left side. Quadratics have to be put into standard form set equal to 0. Keep the coefficient positive in front of your quadratic term. Subtracting w squared would not be a good thing. Bringing this over here is a good thing. Okay, now we've got to factor this, and they should be fairly easily factored things. None of these should be terrible things to factor. Remember that your factors produce the zeros once you set them equal to 0. Your numbers are not -2 and -7. Your numbers are 2 and 7. Now, do they both work? So when I go back to my original sentence, I've got to see if this, in fact, 2 works and if 7 works. I think this case, they both work. Sometimes you get one that doesn't work. Okay, so if I put in 2, I'd have the square root of 18 minus 14, which is 4, which is, okay, that's good. 2 works. If I put in 7, then it's the square root of 63 minus 14, which is the square root of 49. Okay, they both work. There are times when one of them doesn't work. Okay, so we got to be careful to make sure that you check for extraneous answers. And again, if you have a quantity and a radical, this is just a single variable. But if you have a quantity and a radical, you've got more work to do. I think this one's going to produce an icky extraneous. Okay. So now remember what to do with V minus 3. Okay, how about we do this? Get it into standard form set equal to 0. And then we'll look at factoring it. So square both sides and get it into simplified standard form, and then we'll factor it. Here, I'll do this side. I'll do half the work. How's that? I don't know that we are going to generate an extraneous one, but I have a feeling we are. Maybe not. I don't know. And I'm just going to jot down, just you can check real quick. Okay. So that is the squaring of V minus 3. Okay, someone want to give me the standard form version? V squared minus 3V minus 28. That one factors nicely, Ray. Remember your sign patterns. So our answers are 7 and -4. Let's see what happens. My gut says -4 doesn't work. 7 minus 3 is 4. The square root of 37 minus 21 is 16. We'll take that one. -4 minus 3 is -7. And -7 is not going to be equal to the square root of anything over here. Okay, so no, that doesn't work. While it does produce, the square root of 37 minus -12, which is 49, the square root of 49 is not -7. So it generated an extraneous answer. Careful though, too. It's not always the negative one that doesn't work. It could be the positive one that doesn't work. And that's the deceiving thing. So you just have to check. Okay, I do want to just show you the start of, so that's about the extent, just so we're clear. That's the extent at which I would put anything on your quiz that's radical equation related. And it probably won't be a quantity like this. More likely, maybe something like that wouldn't be an impossible thing, or even something that's just basic radical equation. But I do want to address one thing. If you start, I'm going to extend this for you, so don't panic about getting anything in section 7 done. I would look at some of it, but I'll extend it so it goes on for a while. But I just want to address this for those who may feel ambitious to continue to go and get it done. So you notice that you've got a quantity on one side that involves a radical and you got a radical on the other side. So it's impossible to do any type of isolate radical. I'm stuck with a quantity with a radical and a number regardless of what I do, right? I'm not gonna get rid of it. This is a never-ending square both sides, isolate, square again. So when this happens, and again, we'll do this last problem, I'll show you. When you run into this, you've got a radical plus a number or anything else, even maybe another variable. You're still gonna have to square. That's gonna get rid of this. But it's gonna generate another one over here. But then we'll have to isolate it and square again. So when I square this, it's like going through your perfect square pattern. So you're gonna get a y, then you're gonna get 5 radical y, which is 10 radical y, and then you're gonna get 25. I didn't get rid of any, I still have a radical. That's the point. Okay, what happens now? Get rid of that. Get rid of that. Get rid of this. And then you can solve it. Okay? There are worse ones like this. There are worse ones than this that do the same kind of thing in this section. But again, no worries for Tuesday. At the extent, this would be these type of problems in terms of radical equations are the ones that I would be inclined to put one of those on there. I'm not going to put one of those on there. Okay. Any questions about tonight? Okay, so I'll push back the 7 and 8. We'll include the chapter 8 stuff along with the section 8 stuff with the section or chapter 12 stuff. So your quiz on Tuesday will only cover chapter 9 and then 10:1 to 10:7. Okay. And only a little part of section 7. Any thoughts, Hannah, on, well, I guess maybe I should ask those who are in or here right now. Quizzes are what? I usually make them what? 10 problems? 15? They're not very long. They're not that long. Would you guys want to have the first half hour of Tuesday be ask questions, review, take a look at some things before, I'll open the quiz at 6:30 to 7:40 and do that? That sound reasonable? Okay, yeah, I can do that. Let's plan on that. Let's plan on 6 to 6:30 on Tuesday being just a open mic, ask questions, get some stuff answered, and then we'll go from there. We'll open the quiz up at 6:30, and I think it's probably only 10 questions. I'll put a bonus problem on there. It'll be something, So, all right. Hey, have a good night. Stay safe this weekend. Adios, Zoomers.
Bye.
If you have any questions, shoot us an email. Yep, you too. Yeah, we're not doing Halloween.